Okay, so last time we talked about the eutectic system, and this time I want to kind of repeat the same calculations we did before with the microconstituents, except I want to do it now for the iron carbide phase diagram and looking at the eutectoid point. So it's going to be very similar, it's just that all the terminology has changed. All right, so just to remind you again, when you're talking about a eutectic, you're talking about a liquid going to two different solids through this point. Okay, the difference now is we're going to have now a solid, gamma, moving through this point, and it's going to form two different solids. Okay, so that's really the key, is that you have one solid being transformed into two different solids. And the two different solids are going to have very different compositions. And so we're going to have the same difficulties we have with the eutectic case, in that we need to form two different phases with two very different compositions. And so we're going to need to form the eutectoid structure in a layered type format again. All right, so let's go ahead and take a little bit closer look at this diagram. So this is referred to as the iron carbide phase diagram because it does stop at 6.7. So there is a line here at 6.7 that is for iron carbide, Fe3C, which for steels is referred to as cementite. It's a very hard ceramic. It's cement-like, okay, cementite. That's, all right, so that's the one side of the diagram. On the left side, we have iron, and iron at room temperature is referred to as ferrite or alpha iron. Okay, so it's a body-centered cubic structure and has very, very little solubility for carbon. So this tiny region over here is the region for ferrite, alpha iron. And the solubility, the maximum solubility you could have, would be at 727 degrees C, and it would be only 0.022 weight percent carbon. So any more carbon than that, which is most steels, or all steels I should say, have more carbon than that, it's got to precipitate out as another phase. The phase that it comes out is cementite. So we always have a ferrite plus cementite structure. All right, so how do we get the carbon into the iron in the first place so that we can actually get this process of separating out the second phase? We do that by heating the steel up into the austenite region. And this is a gamma iron. It's face-centered cubic now, referred to again as austenite. And that one you can see here at 1147 degrees has a maximum solubility of about 2 weight percent carbon. And so all of your steels are going to be in this range of carbon less than 2 weight percent. And then from there, we'll drop down. Let's say we're sitting here at carbon content of 1.5 weight percent. And then it would drop down, and we would form the ferrite and cementite. All right. If we go up higher and higher in temperature with iron, it would form a delta iron up here that's body-centered cubic again, and then eventually it would just melt at 1538 degrees C. The gamma, that's this picture here, just showing you the single-phase solid solution gamma. You can see the face-centered cubic nature of it because you're getting all of these twin boundaries. So you can see that right in the structure, where the BCC ferrite or alpha iron, you can see here again, single-phase solid solution. So let's get into it a little bit. So if we had a eutectoid steel, that would be a steel that is at exactly 0.76 weight percent carbon. That's right on the eutectoid point here. Or we'll be going through that eutectoid point. And so we would be starting with our austenite, gamma, and we go through the eutectoid point. Upon cooling, we'd enter the ferrite cementite or alpha iron carbide region. And now we have to form these two different phases out of the austenite. And so we'd end up with this layered sort of structure, just like we saw with the eutectic case. The main difference now is in this eutectoid structure, the scale is much, much finer. And you can see here, since overall we don't have all that much carbon in the structure, it tends to look like a ferrite matrix with these sheets of iron carbide. So it looks like a composite, really, right? So we got this nice metal matrix, this soft matrix alpha, and then we've got these layers and sheets of cementite, ceramic. All right, this structure in the steel is referred to as pearlite. So I'm going to try and use that term now. So this eutectoid structure is pearlite. So pearlite is the, I'll say, sheets of ferrite and cementite. So, and we'd have 100% pearlite if we went straight through this point. And just like we saw in the eutectic case, where we had 100% eutectic structure when we went through the eutectic point. And so the similarities here is that in the eutectic system, it's liquid going to two solids. Here, it's a solid gamma going to two solids. All right. And so just like in the other case, we talked about why there were sheets. This also happens in the eutectoid case, forming pearlite, except the difference here now is that since we're in a solid, diffusion is much, much slower. And so the layering in this structure is going to be on a much finer scale to reduce these diffusion paths. Now remember, the alpha has very little carbon in it. And so this is representing carbon trying to diffuse away from the growing ferrite front. And it's moving into the iron carbide, which now needs a lot of carbon. It needs 6%, 6.7% exactly carbon. So again, you get this cooperation, but because of the slower diffusion, you get a much finer scale. All right, so some of the nomenclature, so you can keep that kind of handy when you're working in these systems so that you don't get confused with the different terminologies, because sometimes we'll say ferrite, sometimes we'll say alpha iron. So just keep this kind of handy, but we got austenite, gamma iron. We won't be using the delta ferrite for anything, but it's on here for you. Iron carbide, Fe3C, or cementite all mean the same thing. The pearlite, right? Again, this is your eutectoid structure. It's just always referred to as pearlite rather than eutectoid structure. Iron typically is identified or defined as being less than 0.008 weight% carbon. Remember, we can get as much as 0.022 carbon in iron. And then a steel is anywhere from this value on up to about 2.1 weight%. You can see this note here that's usually less than 1. And then cast irons, which have high carbon, we're not going to talk about with this diagram. We need a different one to deal with the cast irons, and we'll talk about that in a later chapter. All right, so let's say that we are looking at a steel now that has a composition that is less than the eutectoid composition of 0.76 weight% carbon. Since it's less than 0.76, this is referred to as a hypo, right, for less than, hypo eutectoid steel. Okay, so a eutectoid steel is at 0.76. Hypo eutectoid steel would be less than 0.76. And if you're guessing ahead, a hyper eutectoid steel then would be greater than 0.76. So if we look at the structure of a hypoeutectoid steel, then we would start off with a gamma. Okay, this is similar again as the eutectic system, starting off as a liquid. We would move into the two-phase region upon cooling. And this two-phase region now has the gamma, which we started with, plus we'll start getting out some ferrite alpha. Remember, in the eutectic system, this would be a liquid plus alpha region. And the other difference here is in the way that the microconstituents look. So in the eutectic system, since you're forming a solid out of the liquid, you tended to get spherical particles. Now, since we're in a solid, we're looking for the fastest diffusion paths in our material, and those happen to be along grain boundaries. So two advantages of grain boundaries: you can get very rapid diffusion, and the other is that since grain boundaries have higher energy, then by replacing them with a different phase, we can take advantage of eliminating the grain boundary energy. We'll get a phase boundary now instead. All right, so what will happen then is as we move into this gamma plus alpha two-phase region, we'll nucleate the alpha, the ferrite, on grain boundaries, and that's what this picture is showing you here. So they nucleate there, and then they grow. Instead of spherical, they'll grow along the grain boundaries as atoms attach. And so you get what looks like a structure with these, with the grains being decorated with ferrite. And in some cases, if we have a lot of ferrite, then it may eat an entire grain up and transform it into a ferrite. But when we get to this point right here, right before we cross over into the ferrite and cementite region, we could do a tie line in there and figure out what our weight fractions say for this alpha is and what the weight fraction is for the gamma. All right. And as we cross over now and cool below into the two-phase region, just like before where the primary alpha stays and we only transform the liquid, here we're going to call it pro instead of primary, but our pro-eutectoid alpha or ferrite stays, and we only transform, you can see hopefully in this picture here, the gamma. Okay, so the austenite gets transformed into pearlite, that's that layered structure, the eutectoid structure, and our pro-eutectoid ferrite stays. So it's similar again to the eutectic system, just changing really the terminology, and the microconstituents do look a little bit different in a different size scale. But same idea. So let's go ahead and take a look at what that looks like. So if we're trying to identify this in a micrograph, you can see these clear single phase, these solid solution regions, right? So this is going to be all of the pro-eutectoid ferrite that got formed. Right. Again, let me just remind you, this was formed in the gamma plus ferrite region of the phase diagram. And then once we cross over into the two-phase ferrite plus cementite region, the gamma that's left from the previous case transforms into this pearlite. Right? We have a heterogeneous mixture now of ferrite and cementite in sheets or layers. So that's our eutectoid structure. So that's how we can distinguish the two. Just like before, since this pro-eutectoid ferrite is light in contrast, then the light regions in the pearlite is, it would be ferrite in pearlite, are the light regions. And then the dark regions would simply be the cementite in the pearlite. We're separating these microconstituents all out. So now if we're at a hyper-eutectoid steel, so now we're greater than 0.76, we're going to get a similar type thing occurring, except now this region here that we move into is a gamma plus cementite region. So as we move down from the gamma field, we already have the gamma. So what we're going to be forming is cementite when we enter here into this two-phase region. So there's the cementite particles coming out again along the grain boundaries. So in this case, the cementite is our pro-eutectoid phase. Okay, so this would be similar in the eutectic system as beta, say, becoming our phase when we're on the right side of the diagram. Now it's cementite. Now, if I take a look at the full diagram and I imagine a tie line going all the way across out here to 6.7, my fractional amount of cementite is not going to be very big. And so we don't get a whole lot of cementite in this structure. And so it really will decorate the grain boundaries very nicely, rather than eating up an entire grain like we saw with the pro-eutectoid ferrite. So here's a micrograph of that. So now you can see this nice decorating of the boundaries here for the pro-eutectoid cementite. Notice in this micrograph, cementite is now the light rather than the ferrite. So this contrast isn't really due to the phases, it's due to the contrast that's set on the instrument. And so now everything is reversed. That's why you have to identify what your pro-eutectoid phase is first, and then you know what the light regions are in the pearlite then is, in this case, cementite in pearlite. So let's go ahead and calculate these fractional amounts of the microconstituents for, in this case, a hypo-eutectoid steel. Okay, so there's a pro-eutectoid ferrite that's formed, and that's always the case when you have a hypo-eutectoid steel. Okay, and this means, again, less than 0.76 weight percent. All right, so let's go ahead and do this. I'm going to set this all up for you like we've done before. Let me first remind you, because we're only looking at a piece of the diagram here, so just so that we can see this region much better. But do remember this does go all the way over here to 6.7. Right, so let's go back to our full diagram. Here it is. So we're looking at this little region here, right? But remember, this gamma plus cementite region goes all the way out to 6.7, and my ferrite plus cementite region down here goes all the way out to 6.7. So in terms of drawing my tie lines, I need to remember that. So we will be drawing a tie line in the problem that we're doing down here, just below the eutectoid temperature. That's going to run all the way across our sample. Okay, so we're going to have the 0.022 on this end, and we're going to have a 6.7 on that end. So let me go ahead and go back to our problem. Here we are. So let's go ahead and draw that tie line right away. And so again, we're going to go from here, and we're going to go all the way out, right, to 6.7. And we've got the, so I want to go ahead and take this tie line and pull it out like we've done before, so that I can just focus on my tie line. Okay, so on this end, it's ferrite at 0.022. I want to label that. My C0 in this case looks like it was about 0.25. Let's see what it was for this one, 0.38. Okay. So this here is 0.38. And then all the way on the right side, we have cementite right? And that's at 6.7. So that's one of my tie lines. And let me go ahead and we'll label what we know. So if the cementite is over here on the right side, then by the inverse lever rule, we know that the weight fraction of cementite is then this over here on the left side. So that would be this fractional distance. So in fact, let's go ahead and we'll put the numbers in for this. So this is 0.38 minus 0.022. That's that length. And then the entire tie line length is 6.7 minus 0.022. All right. So, and now we know that on the left side of the diagram, we have alpha, the ferrite. So again, inverse lever rule then says that the right side of the diagram is our fractional amount of alpha, or ferrite. Okay, now, just like in the eutectic system, we said that we are in this lower region, that the phase diagram doesn't care about the form or the microconstituent structure. It only cares about a mass balance. And so these are also totals. So this is total ferrite in the entire structure. And this other one is the total cementite in the entire structure. All right, so I've got that. Now let's go ahead and draw our other tie line, right? In these problems, we always need two. So let's go ahead and draw our tie line in this little region in here. Right. Remind you here, because again, this is not labeled, but this is gamma plus ferrite. Okay, so let's go ahead and pull that one out. So here's my tie line. I have alpha over here on the left. And we saw on the previous case, this was labeled in the diagram as being 0.022. We are still at 0.38 overall composition. And now over here on the right side, I have gamma. And that gamma there is at 0.76. Right. So now again, we'll do the inverse lever rule. So alpha is over on the left. So that means this piece here is alpha. And we'll remind ourselves, instead of calling it primary alpha like in the eutectic, it's now referred to as pro-eutectoid alpha. And then gamma is over on the right. So then this piece here is gamma. Now in the eutectic system, we said that any liquid in this upper tie line is transformed into eutectic structure. So the same analogy holds here, in that any gamma austenite that we have here in this upper tie line will turn into pearlite. That's our eutectoid structure. And the pearlite, right, consists of ferrite in pearlite plus cementite in pearlite. So that's all of our microconstituents. So now we can really find anything that we want. We got everything labeled. We have all of our values from our tie line number-wise so that we can find our fractions. And so we could find anything that we need. And the first thing we're going to need, let's say we're looking for the amount of ferrite alpha in the pearlite. Right? How do we get that one? Well, let's just remind ourselves about these equations that we have in that bottom tie line. Total alpha is going to be pro-eutectoid alpha plus alpha in pearlite. Right? And these equations always hold. So we can also write total cementite is equal to the pro-eutectoid cementite plus the cementite in the pearlite. Now, since we are on the left side of the diagram, we only go through this two-phase region of forming alpha from our gamma. And so we don't have any pro-eutectoid cementite. That would be over on the right side. So this one is 0. So our total cementite is our cementite in the pearlite. That's the only place that it is. But in terms of the ferrite in the pearlite, what we're going to need to do to get that is to go ahead and get the total alpha. And we said that was this bottom tie line. And then we're going to subtract from that the pro-eutectoid alpha, which comes from that upper tie line. And that'll give us the amount of alpha in the pearlite, ferrite in the pearlite. All right, so that is all of the microconstituents. All that's really left to do is to plug in the numbers. And so, and I already did one for you here, getting the total cementite. But now they've got all the numbers and the fractional pieces specified. Hopefully you can just plug in the numbers for the rest of these, but everything is there that you need. If you want to get the fractional amount that is pearlite, the eutectoid structure, you could either get the ferrite in pearlite and the cementite in the pearlite and add them. Or again, you could just use the upper tie line and just get the amount of austenite that you have from that piece. And that would be the same as the overall pearlite. All right, and I realize that the hard thing about this particular problem is all of the terminology. So I'm sure every other word I said here, the pearlite, the ferrite, cementite, sounds like you're learning a different language. So again, key is to keep a cheat sheet with you so that you can work through these kinds of problems. You always have at least the main phase diagram for this iron-carbon system, which is this one, which does act as your cheat sheet because it has labeled on it for you austenite, ferrite, and cementite. And it's got all the values like the 0.022, the 0.76, the 6.7, all those values that you need. All right. So that is it for this one. I'll leave it to you to look at the right side. And remember that on the right side of this diagram, if we were at a hyper-eutectoid steel, the main difference now is you're going to be over here somewhere, and the upper tie line you're going to use would be right, this one here, that goes from 0.76 on this end, gamma, over to 6.7 cementite on the other end. And you would no longer have that black tie line there. So just some major concepts in terms of words. So phase diagrams is what we've been looking at. The transforming from one phase to another is something that we're going to get to in the next chapter, chapter 10. And so we have that to look forward to. All right, so I want to go ahead and end there, and hopefully that's enough that you can complete all of your homework at this point.